Have you ever just sat there and counted to 30? 1, 2. Yeah, in human terms, it's basically a short pause. But in the world of computing, 30 seconds is an absolute eternity. Yet as we build these increasingly complex networks of artificial intelligence, 30 seconds is exactly how long you might wait for an AI simply to figure out which other AI it needs to talk to. Imagine trying to run a lightning-fast digital economy, but your master coordinator takes half a minute just to pull up a contact list.
Welcome to this explainer. Today, we're diving into some absolutely fascinating research all about the GRAIL framework. It's a real game changer designed to bridge the massive gap between latency and precision in the multi-agent AI ecosystem. We're going to look at exactly how we can get highly accurate AI routing without those agonizing wait times. Okay, let's dive into this. Our agenda today covers 1. The Internet of Agents, 2. The Agent Discovery Bottleneck, 3. Enter the GRAIL framework, 4. GRAIL's 3 key innovations, 5. Putting GRAIL to the test, and finally, 6. The future of AI agents.
Section 1. The Internet of Agents, the new AI gig economy. So, we're rapidly moving away from the era of the isolated single chatbot, right? We're heading straight into this massive, interconnected gig economy of AI workers. In this new world, we have thousands of specialized multi-agent systems, from coding assistants to financial analysts, all ready to collaborate. But to make this whole shebang work, we rely heavily on what's called agent discovery. This is the critical process of accurately matching your natural language request to the absolute best, most capable agent in a massive pool of candidates. Think of it like the ultimate HR department, except this one actually hires the exact right worker in milliseconds.
Section 2. The Agent Discovery Bottleneck, the Goldilocks problem.
Now this brings us to a major roadblock in the infrastructure. It's basically the Goldilocks problem of routing user intent. Currently, systems generally have to choose between two extremes. On the one hand, we have LLM-centric parsing. This uses massive models, like Gemini or DeepSeek, to really think through your request. It's highly accurate, sure, but this think, then look up approach creates prohibitive latency. We're talking over 30 seconds. On the other hand, we have monolithic dense retrieval. This uses vector databases for millisecond speed, but it compresses an agent's really complex resume into just a single number or embedding. This causes what's known as semantic drift. It totally loses the subtle constraints of your request, resulting in incredibly low precision. So it's either way too slow or way too clumsy.
And this brilliantly illustrates exactly how these paradigms stack up against each other. If you check out the bottom track, that large LLM parsing takes over 4 seconds just for the basic inference, totally dragging out the whole process. The middle track, the monolithic vector, well, it's super fast, but it yields really low precision because of that semantic drift. Now look at the top track. This is our just right solution, combining a fast SLM predictor with fine-grained maxim resonance to achieve both high recall and incredible speed.
Section 3. Enter the GRAIL framework. Speed meets precision.
So, let's look a bit closer at how speed finally meets precision here. GRAIL actually stands for Granular Resonance-Based Agent/AI Link, and it's custom-built to achieve sub-400 millisecond discovery latency. But the big question we have to ask is, how exactly does GRAIL beat semantic drift? How does it avoid this sort of semantic dilution? To really wrap your head around this, imagine a highly specialized expert. If you average out all of their incredibly specific, niche skills into a single overall score, well, they might just look like a generic intern, right? Traditional vector searches do exactly this to AI agents. GRAIL thankfully stops that from happening.
And it pulls us off through a really clever mechanism called maxim resonance. Instead of compressing an agent's capabilities into one blurred average, GRAIL computes the maximum similarity between the user's query and discrete, very specific examples of what that agent can actually do. This is literally a game changer. It means that even if, say, 9 out of 10 of an agent's usage examples are completely irrelevant to your query, if just one single example is a perfect match, Maxim triggers a powerful, highly accurate relevance score. Their highly specific skill isn't diluted by all the others.
Section 4. GRAIL's 3 key innovations, the engine under the hood.
All right, let's open up that hood and see the engine that actually makes all this real-time magic possible. GRAIL essentially decouples the discovery process into 3 distinct deep granularity indices, and these are prepared completely offline. First up, SLM-Enhanced prediction. Second, pseudo-document expansion, which uses an LLM offline to generate synthetic queries that augment an agent's description, making the dense retrieval far more robust. And third, the maxim resonance we just talked about.
So the crucial point here is really that first innovation. Rather than relying on a massive, sluggish large language model in real time, GRAIL swaps it out for a highly specialized, fine-tuned small language model, or SLM, with just 3 billion parameters. This SLM acts as an ultra-fast filter, predicting capability tags in just mere milliseconds.
Now, what's really interesting about this slide is how the architecture maps out the entire factory assembly line. Look directly at phase 1 on the right. This is the offline indexing. Raw agent metadata comes in, and the engine splits it into 3 structured indices: a sparse index for those tags, a context index using the pseudo-documents, and an intent index storing those specific example matrices for MaxSim. And because all this heavy lifting is done offline, phase 2 on the left, the actual real-time discovery driven by the SLM, can happen instantly when a user makes a query. The SLM literally parses the intent in under 30 milliseconds. That is fast.
Section 5. Putting GRAIL to the test. Real numbers, real speed.
Now, theory is great and all, but let's shift to the actual empirical evaluation. Does it really work? Looking at the data here, the researchers tested GRAIL against the baseline LLM router. The LLM method achieved a 78.95% recall accuracy, meaning it successfully found the right agent in its top 10 guesses. Pretty good. But look at that latency. Over 31,000 milliseconds. That's the 30-plus seconds we talked about at the very beginning of the explainer. Now look at GRAIL. The latency plummets to just 394.48 milliseconds. That is a staggering 79 times reduction in latency. But the best part? It didn't sacrifice precision to get there. It actually improved the recall accuracy to 91.45%. It is vastly faster and measurably more accurate.
Section 6. The future of AI agents, scaling to infinity. Let's move to and see how this builds. To get these numbers, GRAIL wasn't just tested in some tiny sandbox, no way. It was pushed to the absolute limit. This word cloud represents Agent Taxo 9K. That's a massive benchmark dataset created specifically to put this framework through its paces. It contains 154 distinct professional industries and exactly 9,240 unique AI agents. As you can see, it covers everything from heavy hitters like environmental science and insurance to incredibly niche specializations like quantum computing and bioinformatics. And GRAIL navigated this incredibly complex, highly specific ecosystem with sub-400 millisecond speed and over 91% accuracy.
Which leaves us with the ultimate question. If GRAIL proves that we can genuinely achieve large-scale, high-throughput, and lightning-fast agent discovery, what happens next? With the infrastructure bottleneck finally out of the way, what happens when not just thousands, but billions of AI agents start collaborating, negotiating, and solving problems together in real time? We are looking at the foundational networking of a true Internet of Agents. It's an absolutely thrilling prospect, and I hope this breakdown helps you understand the underlying architecture that's making it all possible. Thanks so much for learning with me today.